right, we are recording now. This is a new stylus and a long time since I've done this, so bear with me. That's hideous. So I have to fix that. All right. I can show you later what I'm looking at here, so you'll wonder less about why things look like they look on the screen versus what I'm writing on here, because I can't look in both places at once. That's the entire title. I'm not even reducing that for you.
So long.
Okay. So let's have a little chat about area before we go to volume. If I want the area between two curves, tell me how we do that. Top minus bottom, right?
And it might flip.
Yeah.
That's correct, and they may trade places. So some functions, it's going to be more than one region, and when it is more than one region, it quite frequently is the case that the top and bottom trade places. So you have to account for that. How do I know where to? Let's just say I don't have a graph to go by, because I ran into a couple of these on the 1.5 AP Cal exams I did this weekend. If I don't have a graph to go by, how do I know how to set my process up? I'm trying to say it in a way without telling you, so that's why.
You need to know your function.
Okay, function transformations help, but you need more than that. Your what? Okay, well, yeah, obviously you can't do transformations if you don't know the parents.
Are you asking like how to find which one's the top one?
I'm asking how to set up the equation. What pieces of information must I have?
The integral of the top minus
Okay, well, we've already established top minus bottom is the integral of the top minus the integral of the bottom. But you're leaving out a key.
With the integral, like where you're going, you can set the equations equal to each other to get.
Okay, we need to know where the two functions intersect. Yes, the points of intersection become my. It has a name. What are they called when we are setting up our integral? Limits of integration. Yes. I mean, we've only been doing this since chapter 7. What, 3 weeks now? 4 weeks? Oh, Lord help me. Okay. If you look at your assignment sheet, and I don't have one handy, I don't think, but if you look at your assignment sheet, you'll notice that we have 8.3 treated as 2 separate lessons. And obviously your textbook sees it otherwise. But we are going to look at, we're going to look at it as 2 separate lessons, because to me the strategy of each one is slightly different. And I mentioned last week, and I don't know that I actually mentioned this to the whole class, but I had mentioned that I knew there was a handout I needed to give you, but I forgot that it's about volume. Okay, but I don't want to give it to you until after we've discussed it. All right. So let me give you sort of a little challenge question. That's not really a challenge question. It's a to get you thinking in the right direction kind of question. If I handed you a wooden sphere and told you to find its volume without using the volume of a sphere formula, how could you do that? Think like a calculus student. And I will give you a hint. When we started our discussion of integrals, did we immediately start anti-deriving? What did we do before that? Because this is all over the AP exam also.
like the trapezoidal rule.
Trapezoidal rule was the end of that chapter. What came before trapezoids? LRAM, MRAM, RRAM, yes? Okay. So how did I get those, and what does that mean? Rectangles, trapezoids. You're estimating the area by
Dividing up the graph.
right, by splitting the graph. And well, it started out as equal, but then we talked about the fact that Riemann sums, you actually don't have to do that, right? Because we talked about situations where if you narrowed your rectangles in some parts of a graph, you'd get a better approximation than having them all the same width, right? Just because of the lack of uniformity of the shape of the graph. Okay. So we sliced up the area, yes? Discuss amongst yourselves the sphere question I asked you. without using the volume formula and thinking like a calculus student, how might you find the volume of a sphere? Talk to each other.
Like if you're talking like a like when you're dividing those you could do like cylinder. But it's split it all around inward and we used like the cylinder we used like right, the cylinder to approximate.
Shannon.
Didn't it? I thought we used it wrong. You could use like the right. Right. I remember.
Splitting it up into cylinders.
Whatever the height of your cylinder is.
Okay, I'm hearing the word cylinder a lot. Let's get back together as a whole class, and I want someone to explain to me the cylinders. And then we're going to talk about the cylinders because I'm really glad you brought that up, because this traumatizes me every year. There are some classes where it's worse than others. I've actually had classes before where one idiot shared this method and then everybody adopted it, and it was like, what the am I looking at when I looked at your tests, okay? This time, there were only one or two of you, okay? So, cylinders. Talk to me about cylinders relative to my initial question.
Find the volume of each cylinder, like splitting the sphere up into cylinders.
Yes, so basically if we have one of those magical saws that they make where you can just, right? Laser beam maybe?
Like
And slice it,
slice and dice.
okay? Slice it so that we create what are effectively cylinders, but they're not really cylinders because if I slice a sphere, do I actually get cylinders? No, because we have these rounded sides we're dealing with, right?
Yeah.
But the idea is the same. So then if I could, what would make it really easy is if I could slice the sphere up in such a way that the height or the depth, however you want to think about it, of each cylinder was 1,
Right.
right? Because then if my height is 1, what is the volume of my cylinder?
Just the amount of cylinders you
Okay, but if, okay, let's talk about this. The volume of a cylinder is pi r squared h. So if my h is 1,
It's just pi r squared.
it's just pi r squared. In other words, it's the area of the face, right?
Right.
Okay, so if I'm thinking of it as cylinders, I can think of the area of the face times 1 if I set it up so that my height is 1, right? And I was really excited in that back corner, and it may have happened somewhere else, but that's where I heard it specifically, to hear you talking about back when we did LRAM, MRAM, RRAM, there were some 3D problems. And this is the part that blows my mind, okay? If I am using cylinders to approximate the volume, and I'm going to draw for you some of what I saw. I call these the godforsaken pipe organ pipes, that somehow you're going to take this arrangement of cylinders as opposed to, say, if I'm working with a sphere, then I slice it this way, and this is what I use, the analogy I use there is if I take that slice out of that sphere, I'm thinking like a tuna can that's flat and wide, yes? Not, for the love of God, ever this.
Like the layer
And-
layer of a cake.
Yeah, or layers of a wedding cake that Blake so proudly emphasized in those discussions. So, oh God, don't say cake because someone will bring a wedding cake tomorrow.
That's expensive.
Yeah, not if you bake it yourself. So anyway, here's the thing, that you can say this is a possibility tells me that you aren't making sense of things as you go, because that makes no sense. How, on what planet would standing up a bunch of pipe organ pipes ever create a sphere? Especially if they're all standing side by side as if they are still pipe organs. I mean, organ pipes. Yes, you with me? So this one right here, which I'm going to keep, no, that says I don't understand that when I learn things, I should be making sense of them. Because if that makes sense to you, we might want to see if there's somebody that can talk to you for a little while and help you understand that that is not, in fact, how things work. Okay, so you told me, and let's recap. So what we decided together in our little discussions we had is that if I want the volume of a sphere, our first step is going to be slice it, and I know this is sort of abusing the language a little bit, but we're going to go there. All right, slice it horizontally. Yes? Into cylinders. Well, once I did that, then my job would be to do what? Well, okay, area, if I'm smart enough to use, or I'm allowed to use, a delta x, right? That was what it was back then, a delta x of 1. If delta x equals 1, it is the area, but really my job is to determine the volume of each, right? And then what? Add them all together. So we'll call that add them up. Now this is obviously not your notes. This is to get you thinking conceptually about what we're about to do, because it's very related to what we're about to do. And today is the day you find out why 7-1 is 7-1. 7-1 is 7-1 because 8-3 is coming when you do 7-1. Okay? So we're going to slice it horizontally into cylinders, it being the sphere. We're going to find the volume of each cylinder and then add them all up together, right? Okay. And then obviously how we slice them, where we're using an LRAM approach or an RRAM approach or MRAM approach, determines the degree of accuracy of our answer, right? Okay. All right. So, we started in chapter 7 talking about slicing up areas, right? That we extrapolated to a couple of volume problems on that lesson, but we were really just talking about areas. And what did area turn out to be in calculus land? Okay, so area, and we're going to do a two-way implication there. Area implies integral. And our initial approach to it was to take the area, approximate the area using known shapes, yes? And we use triangles, we use semicircles, remember that? Where you were given the ones that had obvious shape to them. And then we broke off into, for random curvy areas, we started thinking about it in terms of using rectangles or trapezoids, right? Yeah. Okay. All right. So, doesn't it make sense that we would use sort of a 3D approach to that? Okay? So what happens in the first part of this lesson, and this is where we're actually getting into the specifics of what we're going to be doing for today and tomorrow. This is volumes of solids of known cross sections. And it's hard for me to gauge how big I'm writing, so bear with me. It's all for faith. I'll give her a little shout out if you want to. Okay. Now, again, to get you thinking in the right direction about this, no, I'll save that one for the second part, because that might make it that might just confuse you at this point. All right. So we talked about what we would do for a sphere. So what if how can I say this to you? I'd really rather not tell you. All right, so if I have a function, this is how this is going to work, okay? So let's say that we have a base that's built on a parabola. So this is my base. Now that will be clearly defined in these problems, and we'll do a couple of those, but I'm trying to, like I said, I'm trying to get you to think conceptually. All right, so I have a flat base. Yes? All right, well, what if I turn that, and now I'm turning that same region into a perspective drawing of it. All right, what if, and I'm going to switch colors here, so bear with me. It's been a while since I've used this. All right, might should make it something a little more contrast than that. All right, so what if I created a shape using that parabolic base, but what made the, oh, that's terrible. Sorry. What if each one was an isosceles triangle that reached from one side to the other so that it stood up like this? All right, well, when I get back here, so now that would be the face of that shape, yes? Okay, and then if I move back here, now it's going to be like this. You with me? Yes, yes. The diagnostic had stuff we haven't learned yet because we're almost done, but not quite. But you will probably see a disproportionate number of these problems when you take the practice exams, aka former exams, because of the fact that if you think about it, what really tests your understanding is lessons towards the end of the material where you're having to put it all together. Does that make sense? Okay, so if I do this all the way back, eventually when I get back here to the vertex of the parabola, what would my triangle look like? It'd be a point.
Yeah.
Yes, if I go far enough back, right? So this is a pretty bad drawing, but do you understand what I'm saying? The shape is made by taking some specified base. Sometimes it's a circle, sometimes it's a semicircle, sometimes it's made from functions. Okay? And then you take a shape that makes the cross section, which is these blue triangles, and the determinant, okay, what would determine the size of the triangle? Where I am on the parabolic base, right? If it's, so let's say this is a parabola, just a standard, let's say it's the parent function, and we're only going from 0 to 9, for instance. Does that make sense? So I'm looking at it sideways, but it would be sitting at the vertex. Its vertex would be at the origin, right? And then it would reach up and we'd stop it at 9, and that's where this line would come in, right? So let's just say that's what that is. Then that's how you would know exactly what your...
Do they tell you that it's triangle?
Yes, yes, and it will be different shapes every time. Sometimes it's a rectangle so that the height is double the base. Sometimes it's a triangle. Sometimes it's a hemisphere. Okay, so it could be, they're not going to go nuts. It's not going to be no heptagons or any of that craziness.
I need the air.
Okay,
the volume of the
not going to be a trapezoid. They're gonna keep that part basic because this involves enough thinking without having to try to think about the random shape they decided to use. Okay, so based on our conversation about the sphere, what would you hope would work?
If you take the area of the volume of the triangles and try to add them together.
The area volume of the triangle?
Yeah, I was trying to.
It's the area of the base times the height.
Okay, and this is where, you know how, you've probably heard me say this before, I'm convinced, and I think I've read research that this is an actual fact, that you either can or can't see 3D inside your head, like you don't think, like you don't think in terms of 3D, right? So one of the things you're going to have to get good at in this section, and not just this little initial lesson we're doing for this 2-part section we're doing, but any of these volume problems you do, your first job becomes describing the shape for yourself, and this is where your talking to each other becomes really important.
Wasn't that
Okay.
like base 1 and base 2 of a trapezoid? Because it's like the in between of the.
I'm not understanding what you're saying. I mean, I understand what you're saying. I'm not sure how it applies to what we're doing here.
It's like if you have like the change in between those two triangles, where they like start.
Okay. All right. Okay. Let me rewind because I see where you're going. But how many triangles would I have if I counted them all? An infinite number, right? And the number of triangles I'm thinking about would be determined by how it's sliced, right? But remember, we talked about the fact that LRAM, RRAM, MRAM, and trapezoidal led us to taking the integral. And what is the integral?
The area. Between the x-axis.
It's the area, but what I'm saying is, how does it use LRAM, MRAM, RRAM?
Oh, it's just
How do Riemann sums work? Because this is important for you to know too.
It's just the LRM, that's the estimate, and then the
Yeah,
integral that we have.
Okay, I get that we have an approximating technique and then we have taking the integral, which is an exact technique. But my question to you is, what was the conceptual connection? Perhaps I should pause the video and let you find that packet I gave you. And let me pause it. So, after that brief intermission, I hope you have found your answer to my question. And let me take you back another step, because you probably ran into this on the diagnostic as well. What is the definition of the derivative?
It's
That's the
limit
The limit as h approaches 0 times 1 over h.
No, pause.
One over-
Ain't no
not
times.
It's 1 over h.
It's the limit as h approaches 0 of.
1 over,
1 over h times f of
1 plus h.
1 plus
minus
yeah.
f of h.
No, minus.
H.
X plus H.
Or over
F of x plus h minus f of x. Yes?
F.
And we wind up with h on the bottom because x plus h minus x is h? Yes? Okay. So that was the definition of the derivative, yes? What corollary did you find in the answer to my question about volume? Or actually integrals in particular?
About how
I hope you looked at the packet because that was the reason I stepped out of the room, so that you would find it and discuss it. And if you can't find it, what's wrong with you?
it was about how like the more partition that you have, the closer it's gonna be to the exact answer.
Okay, we can be a little more technical than that when it's in the study guide.
The limit as n
It was a limit definition. As the number of slices approaches infinity, we get an actual integral, yes? And that's what and I even created the packet so that you'd see how the pieces line up and how that's really all it is to start with. So obviously if that's the case, now that we're moving into volume land, it's the same concept, yes? So back to my triangles, I said, when would I get a more accurate answer? The more triangles I have. So we have that by letting the number of triangles approach infinity, basically, is what we're doing, yes? In other words, it's an integral. Okay, so if I could do that, how could I, let's just say that I could take this 3D object and slice it into these, like, paper-thin triangles. How could I find the volume?
Multiply or find the area of the triangle.
I would have to find the area of each triangle and add them all together. Yes? Which is how we did LRAM, MRAM, RRAM, right? And turned it into an actual integral. Okay? So there's a formula for that. And I'm going to pause, and I hope that you will be able to explain it to me. Okay? So this is the actual definition of the volume of a solid. Devin, do I want to know why your desk was...
No, man, it was not good to do.
It wasn't?
No, not at all.
Some really
If you
interesting...
ask me,
Some really interesting body language when I walked back in the room. All right. Okay, so since the title is the volume of a solid, I'm going to pick up in the definition. So put ... I know you probably can't even see those dots from where you are, but they're cute on my screen. Let me make them a little fatter for you. There's my dots, my ellipses. All right. Of known integrable, and we're going to pause right there. And you're going to tell me what that means.
It can have
Yes, we can take the integral of it, right? Elsewise, this method is not going to work. Okay? Cross-section area which we will refer to as A of x, capital A of x, as in the area with respect to x, from x equals A to x equals B is, and then they tell you in words, but we're going to just go straight and write in symbolic notation. v equals the integral from a to b of a of x dx. That is basically the formula that's going to drive both parts of 8.3. Okay? We're going to focus, as I said, on the initial part of the assignment where we are working with volumes of solids of known cross-section. The remainder of the lesson, which is the primary focus of volume in calculus, is volumes of solids of revolution, which is what will be the second part. Okay? But the second part's a lot easier once you've mastered the first part. Okay? So, how does this match what we just said a minute ago?
If you get it infinitely.
All right, well, in my picture that I drew, that lovely picture, the parabolic base and the triangular cross sections, relate that to this formula. And remember, I specified that we were talking about the parent function that created that parabolic shape. And we went from where to where? 0 to 9. Okay, go.
Alright, so once you take the integral of the area of the triangle, you're basically gonna find that's gonna show you the area of the triangle from the interval 8 to 9 and 1 to 9, and then that's gonna tell you the volume of the base that we have. Well, not the base.
No, you're trying to find. Well, because that relates.
Okay, just relate the a, the b, and the a of x to that problem for me.
0
to 9.
So a is 0, 9 is b.
So then your area, the area of each of those triangles,
Correct.
it's going to be the sum of all of those.
Exactly. Okay? Now, I'm going to have you write these steps. I don't know that I actually normally do. We normally get it from the examples, but we're just going to go ahead and assume we probably should do this. And it's real simple. It's a quick little set of steps, and that way you'll have something to refer back to when you get lost or confused. Let's see if the screen's going to show it well enough. All right. And we're just going to call this the steps. And this is on page 404 of your books, and you don't need to get your books out, but just in case you want to refer back to it at some point, I'm not making this up. All right, so step 1. And obviously, these are the steps. This is what I should see on every problem you do for your homework, for a test, whatever. Okay? So step 1 will be to sketch the solid. And a typical cross section.
That means
Like the triangle, yeah. Yeah, exactly. So my sketch was the two-colored version of the parabolic base. I don't know what I did that. Why I
How do
did
you
that.
spell cross section?
It's 2 separate words. I'm just having trouble squeezing it onto this little space. Because this is what I see while y'all see what you see. Yeah. So I have to like zoom in on the board to find it. I used to try to do it like full size. I'd be writing so big. I'm like, oh my God. So we don't do that anymore. All right, yeah. So for our example we just did, the sketch of the solid would be showing the base in perspective and then drawing the shapes on there. And you can do 2 or 3, but you want to do at least a couple, maybe at least 3. Not just the face one, okay? Because by drawing those other sections in there, you're reinforcing in your mind that the further we go back towards the vertex, the way I drew it, the smaller your triangles would be. And on all of these, at the end, unless it's a sliced off end, and that's not as typical, but you're going to end up with, if you let it follow an actual function into like a vertex, you're going to end up with an infinitely small triangle that's really just a point, right?
Right.
Would have no dimension. All right? So, step 2 is, and it says find a formula for, I'm going to say determine, there's a point on that eye, determine a of x. All right, well, let's pause for a second because I know my honors pre-cal kids are still trying to figure out what all this parentheses thing with that letter behind it is. What? And we're halfway through. So, of course, they're going to watch this next year and go, oh, you were talking about us in that video. Yes, I was. All right, so what does that mean? What is an A of X? Well, obviously, A is for area.
The area in terms of x.
I think, Did you see that? It's a huge, like a huge bird. The shadow was casting. I was like, wow, is that an eagle or something? Maybe an owl? Okay, so A of X. Right, in terms of X. So we're going to have to make a connection between the shape and the function that created the base. That's basically what that involves, okay? And then, and now hopefully you'll understand why I started with all these questions, because A, we need to review, and I know if you did your diagnostic test, you've probably had a little reawakening here. Step 3 is to find the limits of integration. And that works just like it did in Area Land. Because really on this first part of this lesson, it's exactly like Area Land, because you've got to figure out how to describe with limits of integration and whatnot the base of the thing. I don't know why I put integral. I guess I just need to go home. That would be integration. Yes. Don't make me cuss on my video. I don't want to provide evidence of why they should fire me. Okay. Integrate.
Your shirt says been made evidence.
Yes, but that's what I'm saying. I don't want to make it easy for somebody to. Yes, we're going to subpoena your iPad so that we can prove. Or we'll just go to YouTube and take it. All right. Integrate A of X. Period. And this is the last step, and it finishes that statement with to find the volume, which will become obvious as we do examples. Okay? Now, if you skim through your book and you get freaked out by what you see, don't panic when you see things like cylindrical shells, which I nicknamed the Cousy method back when I taught it. But they decided not to make that an AB concept anymore, so I quit teaching it. In fact, I'm not even sure it's a BC concept, but I think it is. So don't worry, we're not doing all of that just because we don't have to. Okay, so your first two problems are numbers 1 and 2. And both of them have parts A, B, C, and D, which is really, each of those is really 4 problems. So we're going to use for our example, our first example, in fact, probably the only example we'll do because it's actually 4 problems for the price of 1. We're going to do number 2. Okay, so you will probably want your books open to page 410. So I will pause and let you get there. One of the cool parts about this lesson is if you get calculus, it's really easy, but when people see you doing it, they think you're a freaking genius. They really do. So, here we go. Conveniently enough, they almost used my base. I didn't even think about that. I forgot that that's how this is on number 2. Okay, number 2 says, the solid lies between planes. Now, you have to get really good at interpreting this language, and y'all, sometimes, your vocabulary is lacking. And if you don't get your vocabulary in check, that means you can't interpret the questions. Anybody run into that while you're taking the diagnostic? You're like, yes. This is why I've tried to harp on it, and will continue to do so until I have you masters of calculus in time for the AP exam. All right, so the solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 4. Okay, when we say planes, those are like our cross sections, okay? So that's important to know. And they draw you these, you notice you don't see pictures as you scan across the next page, right? You've got to get good at seeing these when they describe them. Good luck with that. All right, so we're going from 0 to 4. And I'm not going to draw the picture because it's there in the book. That would be the first step. They kind of did the first step for you. We will draw the cross section in just a minute, okay? So then it says the cross sections perpendicular to the x-axis between these planes run from, and we will write these equations down because they will become important to us, y equals negative square root of x and y equals the square root of x. And if you need to, sometimes, even when they give you the picture, it might help you to understand what it is you're looking at. If you, over to the side, sketch what this would look like in 2 dimensions. Well, if we did that, and you don't have to do it here, if we did that, what would that look like?
The square root of x.
Okay, it'd just be the square root of x, which we should know,
Reflected over the line.
and then its reflection over the x-axis, right?
Just a
Okay.
parabola on the side.
All right, and we're going from 0 to 4. So we already know, yeah, parabola on its side. So a equals 0 and b equals 4. That's going to be our limits of integration. Okay? Now, that's all we can say about the whole problem, and everything that's written right there applies to a, b, c, and d. Okay? So then we're going to part A. And part A says, the cross sections are circular discs with diameters in the xy plane. Okay? So, the first thing you're going to do is put a circle on your paper. And you want to make it big enough to label. That doesn't look very big in scale, so I'm going to undo that and make it bigger. All right, so you want to make a good-sized circle that you can label the parts and whatnot. All right, and here's how I always recommend for you to, I've done this every year I've taught it, okay? Because I think in 3D, so I had to learn how to translate what I'm seeing in my head into what you can see on paper. And if you don't think in 3D and you want to go look at it, you can go online and Google volumes of solids, AP calculus or whatever, and Google it. You will find applets where you can play with that. And at some point I'm going to get really good at having all kinds of links. And I did that when I first started teaching, but the technology has changed so much that the ones I found are probably not even there anymore. Okay? And I've been too busy lately to do anything about it. All right, so you want to imagine that you're taking the shape you see in that picture and you're twisting it so that you're looking at the biggest cross section. Like you're standing on the positive x-axis and you're looking at it. What are you going to see? You're going to see the circle, right? And I'm going to draw a line, and then you're going to tell me what I just drew.
That's the unit. That's 4.
That's where the 4 is, right? So in other words, and this is also something I think is something that, and I think, I don't know that I always taught this, but over time I realized you need it. When you draw your 2-dimensional shape, I don't know why it's doing a select thing. You want to make a dot. It's not letting me make it. There it is. You want to make a dot where the axis would be. So it'll help you orient your thinking, right? So out behind that, I would see the y. If I'm standing on the x-axis looking at this shape from this perspective, the y-axis would be behind it vertically, right? Does that make sense? Okay. So that white dot represents the x-axis, yes? All right. So then my job is to, what's my next step? Because I've drawn the cross section, they drew the shape for me.
Flip it, right? Flip it so your base is.
Okay, I need my a of x. All right, so, and you'll remember from pre-cal when we did word problems, I always told you that anytime there's a geometric shape involved, that you should write the corresponding formula. So we're going to start with a equals pi r squared. And why are we going to do that? Because my a of x is going to come from that, yes? So I know my a of x is going to start with pi, because pi has to be there if you're finding the area of a circle, right? Okay, so what is my job now?
No, orange.
Figure out what r is, okay? In this problem, are all the r's going to be the same?
No.
What do they depend on?
How far down there?
What you're changing.
Radius of the
Okay, the radius of the circle. And if you look at, if you didn't even know why we were doing this problem and you looked at the circular cross section that I drew, what would the radius be?
2.
4.
Well, for this circle, it's going to be 4, isn't it? Or is
No,
it?
It's 2. It's 2.
Wait, no.
Okay, what is the 4 in this picture? That's my x coordinate, right? That's how far I am from the y-axis, yes? And what were our 2 functions?
Square root of x.
Square root of x and negative square root of x. So looking at the picture in the book in conjunction with the cross section we've drawn, what is the radius of this circle in terms of x?
2.
The radius of the circle, because you have to describe it in terms of x. You can't give me an x coordinate. And that, first of all, 2 is not an x coordinate here. 4 is my x coordinate. Okay, what's the specific radius of this circle if it's the one facing me?
I don't know.
You should know. Look at the picture and think for a second. I'm gonna shut my mouth. What is the radius of the biggest circle?
4.
2.
2. Why is it 2?
Because you plug 4 in for x and 2
You
squared
plug
is
4 into the square root of x and we get 2. Yes? Okay? So the radius of that facing circle is 2. Now thinking in constants may get you where you're going, and hopefully with some practice you'll start to recognize what we're doing here. If the white dot is the x-axis, I'm going to put another dot on here and get you to tell me what this is. What is this point?
That's 2, 4.
That is the
4,
point 4, 2. Yes? Because that's where the shape stops. You're stopping at 4, and the square root of 4 is 2. And why are we doing the square root of 4? Because that's the function we're building this on, right?
Yeah.
So what is this measurement in terms of x?
R of x.
Isn't this distance right here, if I'm looking at the picture in the book, the 3D version they gave me, the distance from my white dot to my yellow dot, the white dot is the x-axis, and the yellow dot is the point on the circle. And what's deciding how big these circles are? The functions from which the base is made, right? Okay? But this particular shape runs all the way through that base, right? So that's the basis of the shape in essence. So if I put an infinite number of circles on there, what's that 3D shape going to, how would you describe that to somebody if they can't see? Like maybe the tip of a bullet, because it's rounded at the back, right? So it looks like the tip of a bullet. Does that make sense? So each tiny slice I take would be what? Smaller and smaller and smaller and smaller until I get back to 0, where there would be a theoretical circle of radius 0. Doesn't that make sense? So the size of the circle depends where I am on the square root function between 0 and 4, right? Okay. Now, if I wanted the diameter, what would my diameter be?
You're talking about at 4.
No, like it would be.
It'd just be x squared.
Guess what? Top minus bottom saves the day again. What's my top function if I'm looking at a 2D graph of the base? The square root of x. I'm talking about the base. The base is the parabola looking thing. And it was defined for us explicitly as being the space between what? Square root of x and negative square root of x. Top minus bottom. What is the square root of x minus negative square root of x? 2 square roots of x. Yes? And isn't the diameter always double the radius?
Yes.
Okay. Does everybody understand why it's the square root of x?
Yes.
Okay. So then this is now my a of x, which was step 2. Yes? So now we're going to put it all together because that's literally all we have to do practically. We've actually done the hard part because the next step is in your 1, 2, 3, 4 limits of integration, which we kind of already did because that was stipulated up front, right? And then what's 4? Integrate. So now we're ready to put it all together. So this is the integral from 0 to 4 of pi, which I'm going to put my pi out front. Why am I doing that? Because I can. Yes? Okay. So then this is the square root of x squared. Yes? So this is in essence the same as pi, the integral from 0 to 4 of x dx. And at the top of this, like way back in front of number 1, it says find a formula for a of x of the cross sections. And it doesn't say set it up, but we're going to stop right here because I'm quite confident that if I left you alone for a minute, you could compute this answer, yes. But the answer in the book will be probably just be the a of x. But I want you to go ahead and write the integral to get in the habit of it, but you don't have to actually compute it. You with me?
So that's the answer?
That's the answer to part A. But you can see that the hard part was not the writing of that, it was the figuring it out, yes? Part B. Part B now, you have a new shape. Same base, new shape. Yes? The cross sections are squares with bases in the XY plane. So now we're going to draw our square. That's a terrible side. I'm going to do that one. Okay, that's a reasonable approximation of a square. And if you're not using a straight edge and measuring everything with precision, you can use your geometry skills to indicate that this is in fact a square. Which becomes important because you'll lose track if you draw a really hideous picture and go, wait, what was this thing? All right, so this is a square. And tell me now, in my square, where to put my white dot. What does my white dot represent?
The x-axis.
The x-axis.
Right there
So
at the bottom.
look at right where in the bottom.
On the bottom, in the middle.
So on the bottom of my square, in the center, yes? And this thing is frustrating sometimes. It won't let you write on top of something else very easily. Y'all see it?
Yeah.
So that's where the x-axis is now. And that becomes really important because otherwise, if you can't orient yourself to this two-dimensional cross-section you're drawing, you're going to say stupid things even though you know what you're doing. Does that make sense? You see what I'm saying? All right. So now let's go to our a of x, right? So this is a square, and please don't do base times height because it makes you look like an idiot. S squared. Okay? The area of a square is s squared. So my a of x is, okay, well now what does that mean I have to do? Right. And it might help you to come over here and write, okay, I need to know what my side length is expressed as x.
Is it going to be 2 square root of x?
It is 2 square roots of x. Right? Because
Right.
this measurement is the same as what from A?
That's the radius.
That was the radius in A, right? Okay. Well, now I'm spanning across because the shape is oriented differently. It was not really oriented differently, but just the nature of the shape, right?
Yeah.
Because I want to know how long the side is. And that's kind of like if I wanted the diameter of the last one. Remember? Okay. So my a of x is going to be whatever my side is, which is 2 square roots of x squared. So that's going to be 4x. Yes? So then my integral, which the book doesn't ask for, but I'm going to encourage you to do for practice, is going to be from 0 to 4. And typically the limits of integration are stipulated. Occasionally you'll get a shape that defines it for you, but if it's just a function like they're doing, or a set of functions like they're doing here, then you're going to have, they'll have to define where to stop and start. All right, so I'm going to put my 4 out front, my x inside, because that's what we do with constants, right? So we're done with B. And I think we're ready for C. I think. Therefore I am. All right, C. Part C. Comments on C?
It's just like a triangle, basically.
There ain't no picture. Yes? So that means we got to draw the 3D one here because they didn't do it for us. All right, so we're still in the same base, right? So if you're going to draw it in 3D, you can actually sort of cheat by copying their parabolas in perspective. So we'll do it something like this. Here's my parabola in perspective, and I'm going to draw my coordinate plane in white to emphasize why we're doing the little white dot every time. So this is my positive x-axis, and this is my positive y-axis standing up back here. Or no, that's not right. I'm drawing it in perspective. It's actually this way. Right? Okay? And then we won't put the 0 and 4 because that's the same in all these. And now we have squares with diagonals in the xy plane.
It's just like a triangle.
Yes, so it's going to look like a triangle, and I'll go back to my blue color here. It's going to look something like this, where these are my right angles. Yes? So then when I come over here, I'm going to draw it oriented like a rhombus as opposed to a square. And so now, where does my white dot go?
In the middle.
In the dead center of it, yes? So we're going to put my x-axis coming out there, right? So then this is the plane in which this sits, yes? You see how drawing that horizontal line helps you? And in the previous picture, we didn't draw it because the bottom edge was where it was sitting in the plane, right? If it's not, if it's not sitting, whatever the cross section is, if the measurement of like a side or something is not defining the base, like this one, draw it in there. It'll just help you think about it. All right. So, thoughts, please. Tell me what I know.
Two equal triangles.
Okay, we have two congruent triangles
On top.
where this is true. So if I have two, not only these two congruent triangles, they are two congruent.
Isosceles triangles.
They are isosceles, but there's a better thing to know here.
They're right
They're
triangles.
special. They're special right triangles. 45, 45, 90? So what does that tell me? So of my special right triangle, which is what I have to think about in order to think about this diagonal, yes? Or do I? Well, I don't know. I'm trying to get y'all to jump in here and act like you're part of solving this problem instead of me showing you. Because if you understood A and B, this should be sort of a no-brainer here. We know the side length? Do we? How do we know the side length?
You don't. Not there.
You don't, says Devin. And I concur with Devin.
That's not.
Yeah,
That's
draw
four. That's
lines
not
through the
one.
middle.
What do we know about our... Okay, what do we know about... First of all, let's take another step. This might wake some of you up, because some of you are like, I don't know why she's making a big deal about this. Well, because if you can't think through this, you're kind of in trouble. All right? So let's go ahead and write our area formula. It's s squared. It's still s squared because it's still a square. But the orientation of the square changes the dimensions, doesn't it? Because now, what do I know about my square? I know the length of its diagonal, which is not very handy with what I'm looking for is the side length, yes? So I have to realize that when I draw the diagonal in a square, I create two special right triangles, yes? And that makes this the what? This thing, this white line I drew, what does that make that for the triangle? It's the hypotenuse is 2 on the square root of x. So I have a squared plus a squared equals 2 on the square root of x squared, don't I? So then this is 2a squared equals 4x. So a squared equals 2x. So a, right, it's x. No, the whole thing's in the square root, isn't it? The square root of 2x. Yes? So how do I change my a of s squared, my a equals s squared into an a of x? This is not rocket science, people.
Oh, it would be a of x equals the square root of 2a squared.
And that step needs to be on your paper, because I know there's about 5 of y'all that are still arrogant enough to think that you're smarter than I am, but if I put it in my notes on the examples I'm doing, you need to put it in your work. Okay? So then my actual a of x, after I clean it up, is going to be 2x. And I can be a little sloppy on this problem because we are working between 0 and 4. So I don't have to worry about the potential negative x, because there's not one, right? So it's sort of like the 0 to 4 limits of integration creates sort of a domain restriction, right? So that's that one. So my integral then is from 0 to 4 of 2 on the outside x dx. Ready for D? All right, again on D, they did not draw the picture for us. So we got to do that for ourselves. All right, so now, again, my perspective parabola, and I'm going to put my axes on my picture. It's like you're looking at a page on an angle when you draw that. All right, now our cross sections are equilateral triangles with bases in the XY plane.
That's like what you just did for the first.
That's right. So equilateral means that, like this front one, the sides would all be that size, yes? And I can put congruent marks to emphasize that that's what I'm drawing. You with me? So obviously, as I go further back and draw more triangles, which I'm not going to do in the interest of time, but you should draw, like I said, at least probably 3. A little smaller one towards the back, one in the middle, to remind yourself that these triangles are going to be, as I work from 4 back to 0, they're going to become a lot smaller and smaller and smaller, yes? Until the very last one is not really there. All right, undo. All right, so now what do I need to do? Draw your cross section. Brooke, you sounded so disgusted. Draw your cross section.
And then your center is going to be
On that bottom
or your x-axis.
cross.
Yeah. It's going to be on
Yeah, my x-axis is somewhere right about in here. Yes, I kind of offset my congruent mark there. All right, so that's where, so if you're standing looking at the end of the shape, and to me that really helps orient you to the shape. So, and as you can see, like if you look over at the next page, you're going to have lots of them where you're not given a picture, okay?
So then that's going to be
So what do I write next?
the area.
The area formula. And the area formula for a triangle is 1/2 the base times the height. There is also an area formula for an equilateral triangle that you might want to commit to memory and or store in your calculators if that's an option. But we'll work with this because this is what we know and we're running out of time. All right, so now I need to get an a of x, so that means I have to figure out my base and my height in terms of x.
Your base is going to be the 2 on the square root.
Oh wait, let's not do that. Let's not put the equals there. Let's put the a of x equals. Because I think this helps, just like I tried to get you to do this last year in your pre-cal classes. If you're working from a geometric formula into an x expression or whatever, that you should do it piece by piece. And we do know our base, don't we?
Yeah.
It's 2 square roots of x. Is everybody good with that? And now we got to figure out our height. Not quite such a simple problem. But guess what? Just like if I put the diagonal in a square, I create 2 special right triangles, 45, 45, 90s. This, by definition, being isosceles. No, I'm sorry, equilateral, my bad. Equilateral,
So you know that they'll have
the angles are all equal. So the angles are all
Congruent.
60, because 180 degrees in a triangle. Dear God. Okay. Just me sitting here teaching every math there is all at once while I teach you calculus. That's just such fun. So all of my angles are 60. So when I drop an altitude in, and an altitude, by definition, takes the vertex here and drops a perpendicular line to the opposite side. So that means I do what to my...
Split in half.
I split it into halves.
And now you have a 90.
So I have a 30, 60, 90 now. So if I know my 30, 60, 90s, and I know this is the square root of x, because it is.
Mhm.
Yes? So then that makes this over here 2 square roots of x, and the hypotenuse,
And then you can do
You could do a plus b squared.
you can do the Pythagorean theorem to find.
you could, or you could know your special right triangles, which I highly recommend. And the special right triangle relationship, let me sketch it for you here, is that your short leg is L, your hypotenuse is 2L, and this one is L on the square root of 3.
So x
Conveniently enough now, our L is the square root of x, yes?
Yeah.
So then this is
Square root of 3x.
the square root of 3x. Ding, 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 square root of 3x. So this is the square root of 3x. Yes?
Mhm.
So then my half and my 2 would cancel, so my final a of x then is the square root of x times the square root of 3x. So this is the square root of 3x squared. Yes, that's legal. So then this is x on the square root of 3. So then my integral is 0 to 4. and I'm going to put my square root of 3 out front because I can. And then my inside function is just x dx, and this is this would give me the volume of that solid. And I would do number 4 with you, but I'm afraid we will run out of time. So what I need for you to have done when you get to class tomorrow is all parts of number 1, and if you feel froggy, jump onto number 3. And we will pick up from there. Your assignment sheet delineates the assignments as separate, so do however much you feel equipped to do, and then you should be asking questions tomorrow as needed.